board. You can't ever get, careless and try to cram and stuff like this, because this was an easy quiz. Quizzes are upcoming, they're going to be a lot tougher. I'm just warning you. Try to be fair about it. So today what I'm going to do, before I take questions about the homework, I'm going to go over some properties, because I think this will help take care of all the typical problems. I know the properties. Laplace transforms. I'll just tell you this. Laplace transforms, really, a base set of functional pairs that I put up there. After that, everything else you get, if you're doing the actual Laplace transform, is simply going to be using properties to get what you need. So, by the way, is that solution on OneNote? I put it there? Okay, good. I thought so. Just want to make sure it was there. Now, I got a bunch of problems. First, let me go ahead and put the pairings that you should know. These are the Laplace transform pairs you should know. Follow me? I'm going to put them up there. People ask me about this continuously. So on this side of the board, I'll just put them up. The first one is delta t. You should know that that goes to simply 1. You should know that u of t goes to simply 1 over s. Now, these are not difficult. We did these. Do y'all remember these things, class? All right. And I might as well put the definition of Laplace transform right here. Now, after that, e to the minus at times u of t, that went as 1 over s plus a. We proved that one. I'm not doing anything here that we haven't gone over. I'm just restating things you should know that we'll draw from. With me, class? After that, we also did the cosine of omega naught t times u of t. That was equal to s over omega naught squared plus s squared. And we did the sine of omega naught t times u of t. And that went to omega naught over omega naught squared plus s squared. And really, that's about the pairings you need. Yes?
What does that say? S is equal to...
What?
On the...
S is equal to sigma plus j omega. It's a complex number. It has a real and an imaginary part. Generally, the imaginary part we call the frequency. It's in radians. It's just like the omega you're used to, 2 pi f. And the sigma is something that's a real term that has to do with a decay property, but it really is going to have to do with stability, and that comes in the future. Now, you've had Laplace transform, so these pairings should be very simple. They're things you know, right? Now we talk about the properties, and I'm going to go through a bunch of properties. I want to make sure I put these properties up now before I apply them. I want to get them out. They're in the book. I'll prove some, I won't prove all. Some are obvious. The first thing, if that is the definition of Laplace transform right there, then we can say if we have x of t and it goes as x of s, then if I have a k here, a constant, it just goes as a constant there. That's linearity. And I could make the case if I add plus, say, L times say x2 of t, it would go to L times x of x2 of s. Are you with me? That's just linearity. In other words, if you have a Laplace transform of something, x of t goes to x of s, kx of t goes to kx of s. For instance, delta t goes to 1, 2 delta t goes to 2. With me? And if you had delta t plus u of t, it would go to 1 plus 1 over s. That's it as far as the transforms. With me? I don't want to spend time on that. Everybody? It's straightforward. I do want to spend time on some of the others. Now, this is one we didn't cover. If I have x of at, this is a time scaling. We're going to go through this. You don't have to write this down, but if you care to, you can. I'm not going to do all of them. I'm going to do this one. If If I come over here and I say, now this is the definition of Laplace transform, I want to see what it is for x times, x of not t, but at, right? A is a constant. So that would be the integral from 0 to infinity, x of at, e to the minus st dt, right? Now, here's the job, here's what we're after. We're trying to make this look like this, all right? Now, these are called dummy variables. Anything with the t is integrated out there. Do you all see that? Right? It's what's left behind you worry about. So, to do this, the first thing I'm going to do is create a dummy variable. U is equal to at. That's the argument of x. Then I take a derivative of that with respect to t. And I get du is equal to a dt. I'm trying to be sensitive to that side of the room. I know I blocked it. Are you with me? Now after that, I'm going to go and substitute. You see how dt is du over a? Everybody? dt is du over a, right? So I'm going to substitute this in here, and you'll see this. That means this becomes the integral of x of u times e to the minus s, and then t is equal to u over a, times dt is simply du over a. And I can take the a out here. It would still go from 0 to infinity. Just take a look at what I've done. I've replaced at by u. I've replaced t by simply u over a, right? Can you all see this? Just make sure you see it. Can you? I'm sorry if I'm writing too small, Jeff. I'll try to make it bigger. Are you with me? Now, you can see if s over a was like an s prime there, isn't that really the coefficient right here? Like s is just what? It's the actual argument of the Laplace transform, isn't it, class? Right? And you can see what this really is the Laplace transform. It's like x of u e to the, instead of s prime u du, this is really going to be 1 over a, the a is there, x of s over a, not s, because the s that would be there is really s over a. Do y'all see that, class? How many see that? Now that's a scaling operator, so this is a good one to know. Right? That's scaling. Next is this, and this is something, last time in class, I said something that wasn't correct. So I want to make sure I correct it right now. I'm going to say if you have x of t go to x of s, then x of t minus a times u of t minus a, we're going to do this one. Before I forgot the u of t minus a here. In other words, this is shifting everything over by a. Think of it. If it started before it's 0, x of t, now it's starting at a. Think of it that way, because the u of t minus a is 0 until t is a. So I'm going to come over here and do that one. So when I take a look at this, now I come over here and I'm replacing the x of t by the function x of t minus a, u of t minus a, right? So when I do that, I can say this is really the integral of x of t minus a, e to the minus st, right? Right here, it's still st here times dt, but you'll notice, what does this u of t minus a do as far as the starting point? When is this function actually not 0, or possibly not 0? Class?
At a.
At a. So now the lower limit isn't 0, but it's a to infinity. Are you with me, class? That again is just this integration substituting the function x of t minus a, u of t minus a. Agreed, class? All right, I'm not trying to prolong this, just making sure you all see this. Now what I'm going to do is this, a dummy variable, right? T minus a would be u, and that, therefore, du would be equal to dt. Agreed? That's straightforward. Now make the substitutions. That means this integral becomes the integral of x of u, then it's e to the minus s times t is really u plus a, and then dt is du, right? And because we're integrating with u, you can see if t starts at a, u starts at 0 to infinity. Just take a look at that. The last part of this is du. Y'all agree with that? I'm going to see this right here. Can y'all see what I've done here? A simple substitution, right? Now here's the thing you've got to realize. The integration is with respect to du, right? It's a u. That means e to the minus s times a can come out in front. It doesn't it, class? So that's what I'm going to do right here. Well, actually, I'll put it down below there. That means this is e to the minus s a times the integral from 0 to infinity x of u e to the minus s u du, right? Now what do you see this is? Remember, the t is, I call it a dummy variable. You're integrating that out, aren't you, class? Isn't that the same thing as this, only use the dummy variable? You all see it? Right? And therefore, this is the Laplace transform. Or I can say for this one, it's e to the minus sa times x of s is the Laplace transform of this. So really what this has done is just add that phase in the beginning, or I call it a phase because the SA, e to the minus SA, if sigma 0 is really a phase term. But I don't want you to focus on that. That is the Laplace transform. Got it, class? That's a property. You have to know these properties right here very well. After that, differentiation. Remember, one of the things that this is all based on is this. It's assuming I know this relationship. Some function x of t gives me some function x of s. I know that. From then on, if I have this as the argument, I do that. If I have a time delay operator there, I do that, and so forth. That's what these properties are for. They make life a lot easier to deal with it. So the next thing is dx dt. And I want the Laplace transform of f. Now, again, this is just manipulation. I'll come over here. I'll tell you what, I'll do it right here. I'll leave that up. So if we look at this, what I really want is the integral of dx dt, right, times e to the minus st dt from 0 to infinity. What does that scream of? Something we all learn to hate. Not hate. Integration by parts, does it, class? All right. So if we're going to do this, we see that what? I can say du is equal to dx dt, right, times dt. And I can see that v is equal to e to the minus st. Do you agree with that? I'm just doing integration by parts. Now, that means u is what? U is simply what? X of t, correct, class? Integrate dx dt, right? You get x. And what is dv? Minus s times e to the minus st, right? dt. Isn't it, class? You agree with me? And you know when you do integration by parts, what happens? I'll put this down here. Actually, let me do one thing right here for you, because I have questions about this continually in some form or the other. They don't understand integration by parts. Here's how it starts. If you take a differential of two functions, uv, that's really u times dv, right, plus v du. Isn't it, class? Now, if I want, right, if I want the integral of u, or if I've got u dv, then it's going to be equal to d of uv, right, minus v du is u dv, right? Correct? And then you integrate it. Well, if you integrate a differential, you simply get uv minus this, and this is the integral of v du, is equal to the integral of u dv. The way it's done. And actually, for mine, I have v du on this side. So, and u dv here, so I'll put u dv here, and this is v du. Now, you all understand that? I'm doing that one time because a lot of people with integration by parts don't understand where it came from. It came from actually doing or completing the derivative operator on the differential u, or on the uv term. So now with this one, what happens here? This would be equal to what? Well, it would be equal to u times v, correct, class? Right? uv, which should be x of t, e to the minus st, evaluated from 0 to infinity. And then it's going to be minus the integral of v du, which is x of t, right, times there's a minus s, makes that a plus s, times e to the minus st dt, and it goes from 0 to infinity as well. Do you agree with me here, class? I'm just going ahead and rewriting it. Do you all agree? Now, take a look at the first term for a second. Remember, this is t going to these things. What happens when t goes to infinity, to this quantity, for s having any finite value of sigma? Class? Goes to 0. So it's really going to be minus what? Minus x of t equals 0 minus, right? And here's why. Because when you take subtraction, minus x of t evaluated at 0, I call it 0 minus. It's just as the thing starts, just before it starts. Think of it that way. We're engineers. This is the very first value at t equals 0, just a little bit. And it's going to be times e to the 0, isn't it? E to the 0 is 1. So you got minus x at t equals 0 plus s. And what is this right here? Take a look. By definition, it is the plus transform. Apologies. I think I turned that thing off, but it is. Times x of s. Now I'm going to make a point here. So this is really going to be s times x of s minus x of t equals 0 minus. I've got to make a point about this. Anytime you take a time derivative and you think of the Laplace transform, it always brings an s operator in front of x of x. All right? Usually this term, not usually, a lot of times this is neglected. You don't need that. Are you with me, class? But not always. Now, if you think of this, call this dx dt some new function, x2 of t. Are you with me? I'm just doing that. Now what happens if I take another derivative of this? If I take the derivative of dx2 of t dt, that's the same thing as the second derivative of x of t dt squared, right? Well, then I take this quantity, because that is the x of s of x2, isn't it, class? And then I do the same operation again. So I take s times the quantity, s x of s, minus x of t equals 0 minus, and then it's going to be the value of the function x2 at t equals 0, which is really minus dx dt at t equals 0 minus. And the way the book shows it is this. You can see you're going to get an s squared, x of s, and then it's going to be minus s times x, and this is going to be of 0 minus, and this is going to be, the way the book does it is put a dot over the x to indicate time derivative of 0 minus as well. So now you've got three terms. You've got s squared x of s, then you have s times the value of the time domain function x of t evaluated at t equals 0, then times s, then you have the first derivative of x with respect to t evaluated at 0. Understand? We're going to use all these properties. Understand, class? Are you all with me on this? Okay. I want to get that property out. Now I'm going to keep going. I'm going to use this part of the board for a few more. These properties are what's going to make everything possible. I'd like to leave those up. like in physics, how they have 3 or 4 boards they can shuttle up and down. That's really nice. We don't have that here. Let's see. All right. Now another property that we need. So really, this is the second derivative. These are in your book. Can somebody tell me what page these properties are on, by the way? Anyone? What is it? Page what?
96 or 97.
Thank you. Is that right? Yes. All right. You can just look there. Now, you don't have to write all these proofs. It's important that you see them at least a few times, so when you're doing problems, these things like, they all of a sudden set off bells in your head. This is what I might be looking for. The next one I want to do is going to be t times x of t. So again, it assumes if I have this, then if I have t times x of t, I want the property. This one is really going to go to the definition. I'm going to fuss with it a bit, all right? Think about it. If we know x of t goes to x of s, I'd like to know what tx of t goes to. We did this last time. How many remember that? A couple of you? Do you? I want to do it again for a reason. So if we look at the definition x of s here, x of t times e to the minus st dt from 0 to infinity. Now I look at that and I want the t operator here, don't I? I want t times that. So how might I get it? Well, if I take a derivative of this with respect to s, I bring out a t, don't I? Actually a minus t. So I'm going to go ahead and take the x of s ds, and that would bring it down as an integral of minus s times x of t e to the minus st dt from 0 to infinity. You see, I simply brought down, excuse me, minus t. I simply, when I take a derivative of this with respect to s, I bring out a minus t. Don't I, class? It's this easy. You have to always look at the definition for some of these and then see, well, how can I manipulate it to get what I want in terms of this argument times e to the minus st. Now, yeah.
So you took the derivative of both sides.
Of this and, yeah, of this, which is equal to this, right? I mean, it's an equal sign, right? Mm-hmm. Derivative of this here would be derivative of that with respect to s brings out a minus t, correct?
Also, the derivative doesn't alter the integral at all.
Remember, the derivatives with respect to s, the integration is time, right?
Okay.
So if you could operate on time with the derivative, this is a derivative with respect to s. Here it just brings out the minus t, doesn't it? Now, if you take a look at this and put a minus sign here, you can see this is what we actually want the Laplace transform of. T times x of t. You all see that? But that is it. That means it's minus d ds of x of s. Got some more. Well, for integration, I should have probably done this one right after there, but if I have the integral of x of t prime dt prime from 0 to infinity. Now, if you do this one, let me just tell you this. You see, I want the Laplace transform, is that correct? All right, if I come here, and I go ahead and I put in the integral of the integral from 0 to t of x of t prime dt prime times e to the minus st dt, I want you to take a look at this. Doesn't this look like a u and a dv integration? You all see that? Right. Now when you go ahead and do it, you're going to get du here would just be equal to x of t, and you're going to get v is equal to minus 1 over s times e to the minus st. That's integrating e to the minus st dt. With me? Then when you go ahead and do it and you plug it in, you get uv, which is going to be the integral from 0 to infinity, or 0 to t of x of t prime dt prime, which is u times b minus v becomes a plus times the integral of x of t e to the minus st dt from 0 to infinity. And let me just say what happens. This looks like x of s divided by s. This is right there just x of s divided by s. What happens to this one? When t, if you take a look at this, when t is infinity, this term is 0, right? And then when t goes to the 0, you'll notice the integration just goes from 0 to 0 here, right? Which is 0, isn't it, class? And therefore, this first term is just 0. So the whole point of this, when you do an integration, you get 1 over s times x of s. Now I've got a comment. I'm telling you as a person that's done this for years, things to notice when you're doing Laplace transform theory. A lot of times we do things that are steady state where there's not the initial conditions to worry about. You know when you had your circuits problems? When you did transients, you always worried about the initial condition, didn't you? But if it's non-transient problem, if it's steady state, you ignored the initial conditions because everything was in a steady state of change, you might say. So whenever I'm doing problems, every time I have a derivative operator in time on any function, I think of an s times x of s. Whenever I have an integrator operating in time, I always think of 1 over s times x of s. And this becomes very, very important later with electronic circuitry. Are you with me? How many have heard the term integrator? Differentiator, right? What circuit component usually is used to build those? There's one single, do you know?
Low pass and high pass filter, right?
Operational amplifiers is what I'm looking for.
Well,
Op amps in either differentiator, or you can call it high pass, low pass filter, but as a differentiator or an integrator. And we'll talk more about that later with operational amplifiers. But all this is going to be directly related to electronic circuits that can realize all these functions, all the stuff that we're doing here, the Laplace transforms and stuff like this. You can do all those operations basically with circuits, but I'll spend more time with that later. All right, that property we need. There's the initial and final condition that I'll get on, but here's one property I'm not going to prove, I'm going to show you. It's not that long, but it's long enough to really irritate me in the proofs in the book. Whenever you have this, a convolution of x of t convolved with h of t, this is the one you hate. The convolution operator, right? But why is it so important? It's so important because in circuits, you always say if you're in the time domain and I have x of t coming in here, and the impulse response to the circuit is h of t, the output in the time domain is simply going to be h of t convolved with x of t, or vice versa. Correct, class? That's an extremely important operation. However, if you take the Laplace transforms of everything, then, of this actual operator, then you get x of s here, and you're going to get an h of s here. And the nice thing is, it will be times that, or convolution its time is the same thing as x of s times h of s. It's multiplying in frequency, and that is a super, super big deal. And I'll show you why that's so important in a second. Do you understand that? Instead of convolution, right, here in time, now we can do multiplication. I'm going to do a problem so you will actually appreciate this. Because, I mean, this stuff can drive you nuts. With some of the crazy functional forms you can get. This is easy to do. The question is, when we get to here, well, how do we get back to the time domain? Because that's the realizable domain, the domain that we view, right? And the way is, we do an inverse Laplace transform. How many remember you do that with partial fraction analysis? Everyone should know that. Didn't y'all have, you had your courses here, right? How many had your coursework here in math? Well, if you had your math here, then you had partial fraction expansions, unless you were asleep. Because that's the only way, I mean, that's the big deal with this. We don't have to do all the crazy integrations. I'm going to say there's two other things that I'll talk about later if I have time. One is going to be the initial value, and the other is the final value of a function by looking at the Laplace transforms. And we can talk about that at the end of class. I want to do some problems now with all this information. And before anything, I'm going to show you.
Before you erase that, what was supposed to be on the bottom right in that block diagram? Just H, big H
H of
times.
S times X of S. It doesn't matter
Okay.
the order of the
Thanks, that's
operation.
what I thought.
That's all it is. Now, I want to just do this for you to give you a little sort of peek into where we're going, why it's so important. All right, let's assume I have this. I'm going to have something where I have here, I'm going to have e to the minus 2t u of t coming into something. And here, I'm going to have an h of t. This is my x of t. And I'm going to have my h of t here be equal to u of t, right? Just u of t. And then my output, of course, would be equal to e to the minus 2t u of t convolved with u of t, right? And that's a doable convolution. We can do it. Now we're going to take a look at the Laplace transform operations of these. Laplace transform of this would be 1 over 2 plus s. Do you agree with that? That's the Laplace transform of this. The Laplace transform of u of t is simply 1 over s, right? That means the output would be 1 over s plus 2, or s plus 2, or 2 plus s, times 1 over s. That would be my y of s. I'm going to just show you why it's so important. How many see this right here? I've got the Laplace transform of the h function, Laplace transform of x. I multiply them together, I get the output Laplace transform, correct? And I did not prove the convolution property, but I can if you want me to. Come see me in my office afterwards and I'll do it for you. But I don't want to waste time. It's in the book. All right? It's just one of those things that's, you got to switch the order of operations inside the integrals twice, and it takes a couple of boards, or at least one board. All right, now, do you remember how you do a partial fraction analysis? How many do? Come on, don't do that. I know, Jeff, you do. You live on this, right? All right, let me just show you. You see this s plus 2 here? That's called a simple pole, and you remember that. I'm going to go over this later, but I just want to give you a peek. You all see that 1 over s plus 2 here is something that will go to infinity when you have s go to minus 2. Do you all see that? That's called a pole. A pole is something, a value of s that makes it go to infinity. You also see you have 1 over s here. When s is 0, that goes to infinity, right? So now I'm going to say this can be broken down as any partial fraction expansion that you do, doesn't matter which kind, as some a over s plus 2 plus b over s. Are you with me? You remember this. Now you're all smiling. But see, I don't believe you guys. Because I know you. Now I want to calculate a. Does anybody remember how you calculate a? Multiply everything by the pole, s plus 2. If I multiply everything by s plus 2, that goes away. I get s plus 2 here. And if I multiply by s plus 2, it goes away there, doesn't it? Then I evaluate what's left at s equals minus 2, the pole. When s equals minus 2, doesn't this go to 0? Class? Yeah. And what happens to this? At s equals minus 2, what happens? 1 over minus 2 is minus a half, right? That means a is minus a half. So I'll put it down. I got minus 1/2 over s plus 2. Plus something, call it b over s, is equal to 1 over s plus 2 times 1 over s, correct? I got the first pole, right? How do I get b? Take a guess.
Block I, S.
Multiply everything by s, right? Or the way, it may have been taught this way, this is the way I was taught. You cover up the pole on the left-hand side, because multiplying by s would cover it up, wouldn't it? Get rid of it. and evaluate what's left over here at s equals the pole, which in this case is 0. Do you all see that? Which is the value? 1/2. So b is a half. You'll thank me for what I'm doing here. You all agree? Now that is your y of s. That's your output. But I want y of t. Now we're not there yet, but I'm giving you this peek so you have an appreciation for why you're undergoing this. You're not going to have to do convolution. Now, can you all see what the inverse of this is? What does that look like? What is the function? What gives me a transform of 1 over s plus a? If I have e to the minus at u of t, that goes over 1 over s plus a, correct? What happens if I put a minus 1/2 here? Minus 1/2 there. Correct, class? It scales. So I can say that this term right here, if I go now back to the time domain and do the inverse Laplace transform, this becomes 1/2 minus 1/2 over, or minus 1/2 times what? E to the, people? Minus 2t, go ahead. U of t. Don't forget the u of t. I don't mean to be a stickler about that, but I will be, because you need to do that. Be attentive to that, all right? Make sure you put the u of t in there. What happens to this one? It's 1/2 u of t. And you all see you could write that as simply 1/2 the quantity of 1 minus e to the minus 2t, right? Times u of t. Do you agree with that? All right, now take a careful look at that. What is the value at t equals 0? Class? It's 0, isn't it? E to the minus 0 is 1, 1 minus 1 is 0. What is the value as t goes to infinity? 1, isn't it? You all see that? Now we would find that out if we did the convolution of that. But we wouldn't be happy. I'm just trying to show you that's why Laplace transforms, one of the reasons they're so powerful. They also solve differential equations very easily. Now, I think at this point I got through the information I wanted to on the properties. There's the initial and final values that we'll talk about, but I don't want to focus on that. Now with the homework, any questions about the homework? I gave you a bunch.
You never finished 3.4 yesterday.
Could you give it to me?
X of t equals 12t.
This one. Go ahead.
Either the
4
minus 3 times t minus 4.
times u of.
T minus 4.
All right, I think we can get this in a heartbeat based on the properties. Now listen, and thank you very much. This is actually where, if I look at my notes, I would have start. I want you to take a look at this and just see the things. You see that t operator? Immediately I'm thinking of the property t times x of t goes to, right? Minus d of x of s ds, right? You're right. I'm thinking of that. What about this e to the minus 3t minus 4 u of t minus 4? What is the core, what is the thing that really the essence of that? It's e to the minus at u of t, isn't it? So I'm going to go and I'm going to say first I have e to the minus 3t u of t, and I'll call that x of t. Right? Just call it x. That goes to 1 over 3 plus s. You got to know that. Got to know that like the back of your hand. Understand? Now, what happens when I have x of t minus, in this case, 4? That's e to the minus quantity 3t minus 4 times u of t minus 4, correct? And you remember the property? E to the minus, in this case, 4s, right? Times x of s. How many remember that? If you have your books, do you not remember it, guys? Do you remember we did this just a second ago or not? All right, do you have your books down there? If you do, pull them out and look at the table, because they're there in the table. Bring your books to class. The more visual, you might say, what's the word? Anybody here in the military? There's a word for this. the more exposure, visual exposure, and the more the more times you verbally recite something, the better it is at retention. The military spends a huge amount of money, gazillions of dollars, finding out ways to make people retain things, to think under pressure. They want to make them the smartest and the best they can. And pilots are the worst because they're under extremely high pressures all the time, especially carrier pilots. So they've gone through elaborate amounts of money, I say elaborate, enormous amounts of money to find out what makes people think under pressure and retain stuff. And the continual exposure and repeating what you hear both, and saying it verbally too does. So I'm telling you, these are secrets that I know work. So this one is going to be what? It's just going to be e to the minus, what? 4, right? That's the delayed operator there, right? E to the minus 4s, right? Or 4s here, times this, 3 plus s. Y'all agree with that? Now this, right here, you can think of it as a new function. You could say instead of x of t minus 4, you might as well call that x2 of t. That is the transform of x2 of t. Follow me? Are you with me the way I'm thinking? Now when I take that and I multiply it by t, if I have x2 of t goes to e to the minus 4s over 3 plus s, then what does t x2 of t go to? And the correct response is what? Minus the derivative, right? It's minus the derivative with respect to s of x2 of s, or of the thing above it. Do you agree with me, everyone? How many see this? That's based on a property. Now, if you have your book, look at that property table just for a second. Or if you have it in your notes here. What property is it? I don't know the number. You can tell me. You have it? Somebody's got your book. Don't you have it? Which property is it?
Frequency derivative?
It's derivative with respect to s, but it's really t times x of t goes to which property? Is it 9?
Yes.
Yeah.
9, thank you.
Yeah.
All right, property 9. So now we take a derivative of this. I want you to be careful about this. If I take a derivative of this function here, people make mistakes. You really have two functions, don't you? So the derivative of the first, e to the minus 4s, would be minus 4 e to the minus 4s, right? So it's minus 4 e to the minus 4s times the second, which would be 3 plus s. Do you agree with that? Then you have to take this plus the first, e to the minus 4s, times the derivative of the second. What's the derivative of 1 over 3 plus s? Really 3 plus s to the minus 1, isn't it? And the derivative of that would be minus, right? 3 plus s squared, wouldn't it? So that's going to make this minus, right here. 3 plus s squared. Now remember, that's the derivative of x of s, correct? Right there? What do we have to do with that? Multiply by a minus sign, correct, class? So that gets rid of these minus signs. And that should be the answer in the book. And if you want to, you can do this. You can factor out the e to the minus 4s. And then you could have this be equal to 4 plus 4 over 3 plus s over 1, 3 plus, or s plus 3 squared. And that would, however you want to do it, but that's it. Now, is that the answer that's in the book? Whoever asked this?
Sort of, they multiply it all out.
You can do that's it.
Yeah.
I mean, that's the way you get it. Can we do a few more with these? We've got multiple operations going on. I gave you a bunch of problems. I can pick some, but I prefer they come from you.
B from the same problem.
All right, what is B? Say? Anybody, just tell me what it is.
27t squared,
27t squared,
sine of 60 minus 60.
6t minus
Or in the parentheses, minus 60.
this,
60.
and then u of t?
Yes.
Oh, I'm finished right here.
All right. I'm going to do one of, well, I'll do this problem first, but I'll tell you what we're really looking at. You can do it several ways. You all see here that I didn't introduce the property of modulation yet. I'm about to. And it's a real powerful property. Actually, no, we didn't do modulation. I'm going to show you this. This is important. But if we look at this, can you see that this sine of 60 minus 60 could be rendered as sine of quantity, and then it could be simply 6 times the quantity t minus 10, u of t here, t squared, and the 27 really doesn't do anything except scales, doesn't it, class? That's just a multiplier. If you take a look at that, now we're getting to a point where we can do something. In the book, he literally shows you the transform of sine omega t plus some theta. Do you remember that? He does show you that. So I'm going to start with this. We're going to get the transform This would be easier to do with modulation, but I'm going to do it this way. If we start here, I'm going to say that the sine of 6t times u of t. Now remember I put that up there, right? It's over there, correct? We can do it this way. If we take that, 6 is really omega, so I get 6, right? Over 6 squared plus s squared would be this, correct? Now call that your x of t. Think of it as an x of t. Now do a time delay of minus 10. Right? And now I get x of t minus 10 is equal to the sine of 6 times quantity t minus 10 times u of t minus 10, correct? What does that do? Remember? We just did a problem. Anyone? E to the minus 10, yes, right? So it's going to be e to the minus 10s times the quantity 6 over 6 squared plus s squared. Now we've got that, right? But we have t squared there, not t. Now, I didn't do it for t squared, but in your tables, I'm about out of time. Y'all see we could do it first for t. We could take t times this, right? We could call this some x2 here of t. We could say t times x2 of t would be what? Minus the derivative with respect to s of that, correct, class? And then once we had that, then we take what? That as a function and multiply it by t and just take another derivative, correct, class? In the book he shows that. That's one way of doing this. Would you let me do one thing for you that you'll be thankful for? This is called the modulation property. He does not put it in the book. Write this down. It is a godsend. Now, I know I'm over, but I will be good to you if you let me get this done. Somehow. By the way, we don't have class on Monday unless you really want to. Oh, I can't wait. I'm Lucian. Give me some more.
Are we going to have a quiz on Friday?
Yeah.
Wednesday or any of those days?
Yeah, we're going to have a quiz next Friday. All right, but listen to me. I know we don't have class Monday, so let me finish this, all right? If you have x of t times, and I don't have time to prove it, times cosine of omega naught t. All right, this is real important. This is modulation property. This assumes you know x of t goes to x of s. So write this down. This becomes 1/2 times the quantity x of s, in this case, s plus j omega naught plus x of s minus j omega naught. You can look this up on the internet. It's there, but it's not in our book for some reason. And if you have x of t times sine of omega naught t, this renders as simply j over 2 times x of s plus j omega naught minus x of s minus j omega naught. Now, I don't have time to prove that, but these are two properties that are called modulation, and here's why. With AM radio operations, you take a voice signal. X of t is voice. Highest frequency of interest is about 20,000 hertz, right? Very slowly varying. And you take a very high frequency signal, at say 200 kilohertz, a cosine waveform, and you multiply the two together. Then you get this. And what you're going to see is these are actually the actual transform, the Laplace transform of the voice signal shifted out to the carrier frequency, which is going to be the 200 kilohertz, plus or minus 200 kilohertz. I'm going to talk more about that, but this is the beginning of AM modulation. This is modulation, and we'll talk more about it, and you'll see these things save your life when it comes to transforms. I'll do the rest.
Could you clarify, is that on the bottom, the term out front, is that a J over 2 or a 1?
Yeah, it's a J.
J over 2. Okay.
Yeah, and how about this? I'll send it to you. I'm going to give you some homework for Wednesday. Have a safe safe Labor Day, pardon me. Drive carefully. The police will be out in force trying to make their money.